Alright, so today we're going to talk about the fluid forces and pressures. This is the third part of 8.3, part 3. So we're talking about fluid forces and pressures. So this all comes from Pascal's law, and this is, so the equations that we're going to, the physics equations that we're going to be working with is that pressure is always going to be force divided by an area, okay? The force that goes in, a fluid force, in other words, if I'm in the ocean and I go deeper and deeper, I'm going to have more pressure, right? So the pressure obviously is going to have something to do with the height, right? How the depth, how deep we go, right? So this is going to be equal to the rho h, where rho was the weight density, right? The weight density that we've done before, right? So rho, where are we at? So the weight density is equal to rho this, okay? So basically the equation that we're going to find, if they want to know the pressure or the force, which they're going to ask quite often, they're going to ask for the force, right? Your force is going to be rho h a, okay? So this is basically mostly the equation that we're going to work with here, okay? So let's see if we can do example 3 of Larson's text, and no, this is Anton's text, I guess. Anton's text. 499. So this is this guy here. Okay. So let's see if we can do that. Example number 3. The face of a dam is a vertical rectangle of a height of 100 feet and a width of 200 feet. So we have a dam face that is 100 feet and 200 feet deep, wide, 100 feet deep, okay? So, and find the total fluid force exerted on the face when the water surface is level with the top of the dam, okay? So, let's say that we want to find this guy here, right? If I want to find this guy, right, this is a strip, so I need to find the A. What is the A? A is the area. So the area, if we call this dy, and I call this 0, and I call coming down this way, this height would be y. If I call that y, the area here is what? 200, the length times the width, right? So it's 200 times dy. That would be the A. The rho is what? The rho is, we're given that 62.4. 62.4. And then the height, or the depth from here to here is basically y, right? Y, right? And we're going to go from, well, y is going to go from where to where? From 0 to 100. 0 to 100. Okay? So I can pull these two out. That would be what? So I'm going to get 200 times 62.4 y dy, 0 to 200. 200 times 62.4, 1/2 y squared, and I'm going to evaluate this from 0 to 200. You can plug that in there, right? So that's how you do example number 3. Okay, the one right underneath there is example number 4. Let's see if we can do example number 4. Example number 4, we're putting an isosceles triangle looking thing underneath the water of 3 foot of water, is it? A plate in the form of an isosceles triangle with a base 10 feet and an altitude 4 feet is submerged vertically in machine oil. Oh, in machine oil. Okay, so we have to find the fluid force against that plate. So this was example number 4. So I have an isosceles triangle looking thing down here. And the altitude was 4, and the base here was 10. And I am underneath 3 feet of this oil. Okay? So let's go ahead and we're going to call this guy, okay, this strip here, right? Okay? So if we call this guy here X, okay, so we'll call this guy here X. If this is X, okay, and I want to find the length here, okay, I want to find the length of the strip, right? Because I need the length of the strip to find the area of that strip, okay? So this length of the strip, I'm going to call this guy LX, okay? So the ratio here is this to this is this to this. So X to this, which is L of X, is equal to 4 to 10. 4 to 10. So I'm going to get 10x is equal to 4L of x, which means that Lx is equal to 10 divided by 4x, like such. Okay, so I found an expression for that. So let's go ahead and continue on. I'm going to have, so L of x is equal to 5 over 2x. Okay, so now let's go ahead and put that in the equation that we found, and we're trying to find, again, the fluid pressure. So F is equal to rho H A, right? So the A, the area of this strip is what? The length times the height here, we'll call this dx, right? The little width, height there will be dx, okay? Rho is 30, so this is 30. And what's my h? What's my height from here to this strip? Is 3 plus x, right? So I'm going to have 3 plus x, right? And x is going to go from 0 to 4. 0 to 4, so I'm going to go pull these guys, these two out. This is what? 150 divided by 2, so that's 75. And I'm going to have 3 plus x, and I have this x, dx from 0 to 4, 75. I get 0 to 4, 3x plus x squared, 75 x squared, 1/3 x cubed, evaluated from 0 to 4. Right? You just go ahead and plug and chug that, right? Okay. So that's how you would do that one. All right. So now let's go to your text, your actual textbook, and talk about the Great Molasses Flood of 1919. Okay. So that one. That one actually is, it's an example 4. But example 4 from your textbook, the molasses barrel. So let's talk about the molasses barrel. So there is what is this? This is a metal tank, a cylindrical metal tank. Okay, it is 30 feet. No. It is 90 foot in diameter, and the height is 90 feet also. Okay? Given that the tank is full of molasses, weight of 100 pounds per feet cubed, what is the total force exerted by the molasses on the bottom of the tank when it ruptured? So, A, the force would be, again, this, where rho was 100, right? And the height that is exerting on the bottom is actually the height of the tank, which is 90 feet. 90 feet, so that's the height. And the bottom is 90 feet in diameter, so the radius is 45 pi r squared, right? Just go ahead and pull that, so whatever that may be, 9,000 times, I don't know what 45 squared is, 45 squared, 2025 pi, and whatever that is, okay? B. In B, it wants us to, what is the total force against the bottom foot wide band of the tank wall? So in other words, you have a tank that looks like this, and we want to know the total force on this bottom band here, the bottom 1 foot, okay? So the bottom 1 foot. So if I actually kind of do like the cylindrical shells, and I cut this and bring it open, I'm going to actually get a strip that's going to look like this. This is going to be 1 foot, right? Because this is 89 to 90, right? And I'm going to have a dy here, right? And so I need to find this length here, to find the area of the strip. What's the length? The length is, this is 2 pi r, right? Because it's a circumference, right? The circumference. So it's going to be 2 pi r, so it's going to be 90 pi, basically, because 90 is the diameter, right? 90 pi. So we're going to have force is equal to rho J. So A is what? The area of this strip. So it's going to be 90 pi times dy. Okay. And we're going to go from here. This is going to be 89. This is going to be 90, right? So we're going to call this guy y, right? So we're going to have what? It's going to be 89 plus, so we're going to have, all right, wrong way. So we're going to go y, right? So the y is from, actually y is not from here to here, y is going to be from the top all the way to the bottom. So if I erase this, from here to here would be y, okay? Here to here is going to be y, right? Because that's the total amount of pressure. So you're going to have the height is going to be y, right? So that would be the height, and then we're going to have the rho. Rho was 100, right? And y is going to go from 89 to 90. 89 to 90. So this is 9,000 pi. All I have left is y dy, 89 to 90. 9,000 pi. 1/2 y squared, evaluated from 90, 89. Okay? And whatever that you find there would be the answer. All right? So that would be that 4. And last but not least, let's go to Larson text. And the Larson text, let's do page 468. 468, okay? The one that has that little window, circular observation window there, okay? So let's do that one. That's example 3. Example number 3, so we have water and like that. And a circular observation window on a marine science ship has a radius of 1 foot. Radius of 1 foot. Center of the window is 8 feet below the water level, so up here would be 8. Okay. is shown water. So what is the rho for water? The rho for water they're saying is 64 for seawater is 64 pounds per cubic foot. And we're going to find the fluid force on the window. Fluid force on the window, so E, we're going to go ahead and put a strip like that. So this will be dy. The thickness will be dy. So this guy here is going to be your x, right? So from here to here is going to be your x, right? So this strip is going to be 2x. So you're going to have 2x times the width, which is dy, and that's your area, right? So force, again, we're doing force is equal to rho HA. So this is going to be my area. My rho was 64. Then my height was what? Height is what? My height is, so this is, if we call this will be y, right? This will be y. So my height is 8. And I'm going to take away the y, right? So, because I'm looking for this height right here. So it's going to be 8 minus y. Okay, and I'm going to go, y is going to be from where to where? Negative 1 to 1. Negative 1 to 1. Okay? Where x squared plus y squared is equal to 1. So x is going to be equal to 1 minus y squared. So I'm going to go ahead and put that in there, negative 1. Let's pull the 2 times 64 out. That'll be 128, 128, 0 to 1. And I'm going to have then this x times 8 minus y. So x is that guy. I'm going to have 8 minus y times root 1 minus y squared dy. Okay. Well, it's kind of bad here. All right. You have 8 minus y. And you have this guy. So let's see what happens. Let's take a look at this. I get 128, and I'm going to have negative 1. If I just pull the 8, do the 8 first. 8 times 1 minus y squared dy. Right? And then I'm also going to have to subtract 128 y, 1 minus y squared dy. Okay, I just went ahead and multiplied that out and separated the two together. So I just separated them into two separate integrals. Okay, let's look at the first one. If I pull the 8 out, if I go ahead and pull the 8 out over here, right, I'm going to have 8 times that, right? And what is this? This is the area of a semicircle, right? Because I'm going, and then from negative 1 to 1, the integral of 1 square root of 1 minus y squared. So it's actually from here to here, this area under that curve right here. So it's going to be half of a semicircle, right? So this actually is what? This actually is pi r squared divided by 2. Pi times r squared divided by 2. And I'm done. Right? I don't have to do the integral. All right? I don't have to actually do the integral out. Okay? This guy, if you actually graph this, this graph looks like this. Okay? In other words, if I graph from negative 1 to 1, what's going to happen? This is a symmetrical across the origin. So this guy is going to cancel out with this guy. In other words, this entire term goes away. All right? Leaving you with nothing more than this. Okay? So this is going to be, I don't know, 4 times 128 pi, whatever that is, right? And it is 512 pi. So it's going to end up with 512 pi. So your answer is going to be 512 pi. Okay, so the way to handle the fluid force questions is always look at a strip, find the area, and then use the F is equal to rho HA. Okay, this is what you're looking for. Okay, rho is going to be given to you. This is just a constant. Okay, so you have to come up with a this one would be 8 minus y. You have to come up with an expression for h, and you also have to come up with an expression of a. Okay, and the dy part is always going to be easy. It is the other stuff, like in the isosceles triangle, how that strip, you have to define that. Okay, and that's all for today.